The cosmic tapestry, unraveling, the mysteries of time and space. Imagine a fabric that weaves together the very essence of existence, a fabric that stretches across the vast expanse of the universe, binding together space and time in an intricate dance. This is the cosmic tapestry, a mysterious and awe-inspiring realm that has captivated human imagination for centuries. From the swirling vortex of black holes to the majestic sweep of galaxy clusters, the universe is a realm of breathtaking beauty and profound mystery. And at the heart of this mystery lies the enigmatic relationship between time and space. We measure time with clocks and calendars. But what is time, really? Is it a human construct, a way of making sense of our experiences, or is it a fundamental aspect of the universe, a dimension that governs the behavior of stars and galaxies? Albert Einstein's theory of relativity revealed that time and space are intertwined as a single entity, space-time. But what does this mean for our understanding of the universe and our place within it? The cosmic tapestry is a mystery that continues to unfold. Join us on this journey of discovery as we unravel the secrets of time and space and explore the infinite wonders of the universe. Time dilation, the phenomenon where time passes at different rates depending on speed and gravity, is explained through everyday examples. You'll learn how this seemingly abstract concept impacts your daily life and the universe around you. Time dilation is a fundamental concept in physics, particularly in the theory of relativity. It describes how the passage of time is relative and can vary depending on the observer's frame of reference. According to Albert Einstein's theory of special relativity, time dilation occurs when an object moves at high speeds, approaching the speed of light. The faster the object moves, the more time slows down relative to a stationary observer. There are two types of time dilation. 1. Special relativistic time dilation. This occurs when an object moves at high speeds relative to an observer. Time appears to pass more slowly for the moving object. 2. Gravitational time dilation. This occurs when an object is in a strong gravitational field, such as near a black hole or a neutron star. Time appears to pass more slowly near the massive object due to its strong gravitational field. Time dilation has been experimentally confirmed in various tests, including particle accelerator experiments, where high-speed particles experience time dilation, GPS satellite experiments, where time dilation caused by both special relativistic and gravitational effects must be accounted for to maintain accurate positioning, astronomical observations, where time dilation effects have been observed in the vicinity of black holes and neutron stars. Time dilation is a mind-bending concept that challenges our classical understanding of time and space. It has far-reaching implications for our understanding of the universe, from the behavior of high-speed particles to the nature of black holes and the universe itself. Time dilation, a relatable explanation. Imagine you're on a train, and you throw a ball straight up in the air. To you, on the train, the ball goes up and comes down, following a straight path. Now, imagine someone is standing outside the train, watching you throw the ball. From their perspective, the ball doesn't follow a straight path. It looks like it's moving in a curve because the train is moving really fast. This thought experiment illustrates the concept of time dilation. According to Einstein's theory of relativity, time is relative and can appear to slow down or speed up depending on your frame of reference. Here's another analogy to help you understand time dilation. Picture a spaceship traveling close to the speed of light. Inside the spaceship, time passes normally for the astronauts. They eat, sleep, and work just like they would on Earth. However, for an observer watching the spaceship from Earth, time appears to pass more slowly for the astronauts. This means that when the spaceship returns to Earth, the astronauts might have aged a few years, while decades or even centuries might have passed on Earth. Time dilation is a real phenomenon that has been observed and confirmed in various experiments. It's a mind-bending concept that challenges our classical understanding of time and space. The concept of space-time, gravity's impact on time. Space-time is a fundamental concept in modern physics, describing the fabric that combines space and time. This four-dimensional entity is the backdrop for all physical phenomena, and its curvature plays a crucial role in our understanding of gravity and its effects on time. What is space-time? Space-time is a mathematical model that describes the universe as a unified, four-dimensional entity. It combines the three dimensions of space, length, width, and height, with the fourth dimension of time. This fusion of space and time allows us to describe the motion of objects and the behavior of physical systems in a more comprehensive and accurate manner. Gravity's impact on space-time. According to Albert Einstein's theory of general relativity, gravity is not a force that acts between objects, but rather a curvature of space-time caused by the presence of mass and energy. The more massive the object, the greater its gravitational pull, and the more space-time is curved around it. Imagine space-time as a trampoline. Place a heavy object, such as a bowling ball, on the trampoline, and it will warp and curve, creating a depression. This curvature represents the gravitational field of the object. Now, roll a marble nearby, and it will follow the curvature of the trampoline, moving along a curved path that we experience as gravity. Gravity's effect on time. The curvature of space-time caused by gravity has a profound impact on time. According to general relativity, time is relative, and its measurement depends on the observer's frame of reference. The stronger the gravitational field, the slower time passes. This phenomenon is known as gravitational time dilation. Gravitational time dilation has been observed in various experiments, including gravitational redshift, the frequency of light emitted from white dwarfs, or neutron stars is shifted towards the red end of the spectrum due to the strong gravitational field. GPS and gravitational time dilation. GPS satellites must account for gravitational time dilation caused by their position in a weaker gravitational field. If not corrected, this effect would result in positional errors of up to 10 kilometers per day. Gravitational time dilation in black holes. The extreme gravitational field of a black hole causes time to slow down significantly near the event horizon. This effect becomes more pronounced as you approach the singularity at the center of the black hole. The concept of space-time and its curvature due to gravity has revolutionized our understanding of the universe. Gravitational time dilation, a consequence of this curvature, demonstrates that time is relative and dependent on the observer's frame of reference. As we continue to explore the universe and push the boundaries of human knowledge, our understanding of space-time and its intricate relationships with gravity and time will remain a cornerstone of modern physics. Time dilation in the Milky Way. Einstein's relativity, the foundation of time dilation. In 1905, Albert Einstein revolutionized our understanding of space and time with his theory of special relativity. This groundbreaking concept transformed the way we perceive the universe, introducing a new paradigm that challenged long-held assumptions. At its core, special relativity is based on a simple yet profound principle. The laws of physics are the same for all observers in uniform motion. This fundamental principle asserts that the laws governing the behavior of physical systems remain invariant, regardless of the observer's state of motion. In other words, whether you're standing still, moving at a constant velocity, or accelerating, the laws of physics remain the same. Key implications of special relativity. The speed of light is constant. The speed of light in a vacuum is always constant, regardless of the observer's motion or the source of light. This led Einstein to introduce the concept of space-time, where space and time are intertwined. Time dilation. Time appears to pass differently for observers in different states of motion. Time dilation occurs when an object moves at high speeds relative to an observer, causing time to appear to slow down for the moving object. Length contraction. Objects appear shorter to an observer when they are in motion relative to the observer. This effect becomes more pronounced as the object approaches the speed of light. Relativity of simultaneity. Two events that are simultaneous for one observer may not be simultaneous for another observer in a different state of motion. Equivalence of mass and energy. Mass and energy are interchangeable, as expressed by the famous equation E equals mc. Experimental verification and impact. Special relativity has been extensively tested and confirmed through numerous experiments, including 1. Michelson-Morley experiment, 1887, tested the speed of light in different directions, providing evidence for special relativity. 2. Kennedy-Thorndike experiment, 1932, verified time dilation and length contraction. 3. Muon experiments, 1960s, confirmed time dilation in high-speed particles. The impact of special relativity has been profound, influencing particle physics, understanding high-energy particle interactions and behavior. Astrophysics and cosmology, describing the behavior of celestial objects and the universe as a whole. GPS technology, enabling accurate navigation and timing by accounting for relativistic effects. Einstein's theory of special relativity has revolutionized our understanding of space, time, and the laws of physics. Its fundamental principle, that the laws of physics are the same for all observers in uniform motion, has far-reaching implications for our understanding of the universe and the behavior of physical systems. GPS satellites and time dilation, a critical component of accurate navigation. The Global Positioning System, GPS, relies on a network of satellites orbiting the Earth to provide accurate location and time information. However, the satellite's high-speed motion and altitude introduce relativistic effects, particularly time dilation, which must be accounted for to ensure accurate GPS operation. Satellite speed and altitude, a relativistic environment. GPS satellites orbit the Earth at an altitude of approximately 20,000 kilometers, moving at a speed of about 14,000 kilometers h. This high-speed motion, combined with their altitude, creates a relativistic environment where time dilation becomes significant. Time dilation effects on GPS satellites. According to special relativity, time dilation causes time to pass more slowly for the GPS satellites relative to Earth-based observers. This effect, although small, is crucial for accurate GPS operation. Gravitational time dilation. The weaker gravitational field at the satellite's altitude causes time to pass faster than on Earth. This effect is about 38 microseconds per day. Special relativistic time dilation. The satellite's high-speed motion causes time to pass more slowly, resulting in a time dilation effect of about 7 microseconds per day. Accounting for time dilation in GPS. To compensate for these relativistic effects, GPS satellites' clocks are adjusted to match Earth-based clocks. This adjustment ensures that the satellite's clocks remain synchronized with Earth-based clocks, providing accurate location and time information. Clock correction. GPS satellites' clocks are corrected by about 39 microseconds per day to account for the combined effects of gravitational and special relativistic time dilation. Regular clock synchronization. GPS satellites' clocks are regularly synchronized with Earth-based clocks to ensure accurate timekeeping. Consequences of ignoring time dilation in GPS. If time dilation effects were not accounted for in GPS, the consequences would be significant. Positioning errors. Ignoring time dilation would result in positioning errors of about 10 kilometers per day, rendering GPS inaccurate for navigation. System failure. The accumulation of these errors would eventually lead to system failure, as the satellite's clocks would become desynchronized with Earth-based clocks. The accurate operation of GPS relies on accounting for the relativistic effects of time dilation. By correcting for these effects, GPS satellites provide precise location and time information, enabling a wide range of applications, from navigation and mapping to precision agriculture and scientific research. Time dilation on jet planes, a minuscule but fascinating effect. As passengers embark on long-haul flights, they might not realize that they are experiencing a phenomenon that challenges our classical understanding of time dilation. Although the effect is incredibly small, it's fascinating to explore how time dilation affects passengers on jet planes. The principle of time dilation. According to Einstein's theory of special relativity, time dilation occurs when an object moves at high speeds relative to an observer. The faster the object moves, the more time slows down relative to the stationary observer. In the case of a jet plane, the passengers and the plane itself are moving at high speeds, which causes time to pass slightly slower for them compared to people on the ground. Calculating time dilation on a jet plane. Let's consider a typical long-haul flight, such as a trip from New York to London. Assuming a cruising speed of approximately 915 kilometers h, 567 miles per hour, we can estimate the time dilation effect. Using the Lorentz factor, which describes the amount of time dilation, we can calculate the time difference between the passengers on the plane and people on the ground. For a 7-hour flight, the time dilation effect would result in a time difference of approximately 38 microseconds. Yes, you read that correctly, 38 microseconds. This means that, relative to people on the ground, the passengers on the plane would experience time passing about 38 microseconds slower during the 7-hour flight. Practical implications, or lack thereof. While the time dilation effect on a jet plane is intriguing, it's essential to note that it has no practical implications for passengers or the flight itself. The difference is incredibly small, and it would take an enormous amount of time, pun intended, to accumulate a noticeable difference. However, this thought experiment does illustrate the fascinating consequences of special relativity and encourages us to think about the strange and counterintuitive nature of time itself. Time dilation on jet planes is a real effect, albeit an extremely small one. While it might not have any practical implications, it serves as a reminder of the fascinating and complex nature of time and space. As we continue to explore the mysteries of the universe, we may uncover even more surprising and intriguing phenomena that challenge our understanding of reality. High-altitude clocks, the effects of gravitational time dilation. Atomic clocks are incredibly accurate timekeeping devices that rely on the vibrations of atoms to measure time. However, Even these precise clocks are not immune to the effects of gravity. According to Einstein's theory of general relativity, the stronger the gravitational field, the slower time passes. This phenomenon, known as gravitational time dilation, causes atomic clocks at different altitudes to tick at slightly different rates. The gravitational time dilation effect. Imagine two atomic clocks, one located at sea level and the other at a high altitude location, such as a mountaintop. Both clocks are identical and start ticking at the same time. However, due to the weaker gravitational field at higher altitudes, the clock at the mountaintop will tick slightly faster than the clock at sea level. Calculating the time difference. To calculate the time difference between the two clocks, we can use the following formula: delta t equals g asterisk h c carry 2, where delta t is the time difference between the two clocks. G is the acceleration due to gravity, approximately 9.8 m s carry 2. H is the height difference between the two clocks. C is the speed of light, approximately 299,792,458 m/s. Using this formula, let's calculate the time difference between two atomic clocks, one located at sea level and the other at an altitude of 4,000 meters, approximately 13,124 feet. Assuming a height difference of 4,000 meters, the time difference between the two clocks would be delta t approximately equal 38 microseconds per year. This means that the clock at the mountaintop would tick approximately 38 microseconds faster per year than the clock at sea level. Practical implications. While the time difference between atomic clocks at different altitudes may seem insignificant, it has important implications for various fields, including 1. GPS technology. GPS relies on accurate timekeeping to provide location information. Gravitational time dilation effects must be accounted for to ensure accurate positioning. 2. Scientific research. High-altitude clocks can be used to study gravitational time dilation effects, providing valuable insights into the nature of gravity and space-time. 3. Timekeeping and synchronization. Accurate timekeeping is crucial for many applications, including financial transactions, telecommunications, and scientific research. Gravitational time dilation effects must be considered when synchronizing clocks at different altitudes. In conclusion, the effects of gravitational time dilation on atomic clocks at different altitudes are a fascinating demonstration of the complex and subtle nature of space-time. While the time differences may seem small, they have important implications for various fields and remind us of the importance of accurate time keeping in our increasingly interconnected world. The twin paradox, a mind-bending thought experiment. Imagine two identical twins, Alice and Bob. They are 20 years old and have always been inseparable. One day, they decide to conduct a thought-provoking experiment that will challenge our understanding of space, time, and relativity. The experiment. Alice decides to embark on a journey through space, traveling at 90% of the speed of light, approximately 270,000 kilometers (s), to a distant star system. Meanwhile, Bob stays on Earth, waiting for his twin sister to return. From Bob's perspective on Earth, time passes normally. He celebrates his 21st birthday, and then his 22nd, and so on. However, for Alice, time passes differently. Due to the effects of time dilation, time appears to slow down for her relative to Bob on Earth. The paradoxical reunion. After 5 years have passed for Bob on Earth, Alice returns from her journey. However, due to time dilation, only about 2.5 years have passed for her. This means that Alice has aged to 0.5 years, while Bob has aged 5 years. The twins are now no longer the same age, despite being born at the same time. This apparent paradox raises intriguing questions about the nature of time, space, and aging. Resolving the paradox. The twin paradox is often misunderstood as a genuine paradox, but it's actually a consequence of special relativity. The key to resolving the paradox lies in understanding the concept of relative motion and the asymmetry between the twins' experiences. 1. Relative motion. The twins are in relative motion, with Alice moving at high speed relative to Bob. This relative motion is the key to understanding the time dilation effect. 2. Asymmetry. The twins' experiences are not symmetrical. Alice accelerates to high speed, decelerates, and then accelerates again to return to Earth. Bob, on the other hand, remains on Earth, experiencing no acceleration or deceleration. This asymmetry is crucial in resolving the paradox. Conclusion. The twin paradox thought experiment highlights the strange and counterintuitive nature of time dilation. While it may seem paradoxical at first, the apparent discrepancy can be resolved by understanding the principles of special relativity and the asymmetry between the twins' experiences. The twin paradox serves as a reminder of the importance of considering relative motion and the complexities of space-time when exploring the mysteries of the universe. Time dilation and the aging twin paradox. As we explore the twin paradox, let's dive deeper into the effects of time dilation on the twin traveling in the spaceship. Time dilation, a consequence of special relativity. According to special relativity, time dilation occurs when an object moves at high speeds relative to an observer. The faster the object moves, the more time slows down relative to the stationary observer. This effect becomes more pronounced as the object approaches the speed of light. The spaceship twin's experience. Let's consider the twin, Alice, who travels in the spaceship at 90% of the speed of light. From her perspective, time passes normally. She experiences the usual flow of time, with one day blending into the next. However, from the perspective of her earthbound twin, Bob, time passes differently for Alice. Due to time dilation, time appears to slow down for Alice relative to Bob. This means that Alice will experience time passing more slowly than Bob, resulting in a difference in their ages when Alice returns to Earth. Calculating the age difference. To calculate the age difference between the twins, we can use the Lorentz factor, which describes the amount of time dilation. The Lorentz factor is given by gamma equals 1, SQ or T, 1, V carried 2, C carried 2, where gamma is the Lorentz factor, V is the velocity of the spaceship, 09 C in this case, C is the speed of light. Using this formula, we can calculate the time dilation factor, which is approximately 2.29 for the spaceship twin. This means that time passes about 2.29 times slower for Alice than for Bob. Aging difference. A numerical example. Let's assume that Alice travels for 5 years from her perspective. Due to time dilation, this corresponds to approximately 11 for 5 years from Bob's perspective, 5 years x to 0.29. When Alice returns to Earth, she will have aged about 5 years, while Bob will have aged approximately 11 for 5 years. This means that Bob will be about 6.45 years older than Alice when they reunite. Conclusion. Time dilation plays a crucial role in the twin paradox, causing the spaceship twin to age slower than their earthbound twin. This effect, although seemingly counterintuitive, is a direct consequence of special relativity and has been extensively experimentally confirmed. The aging difference between the twins serves as a poignant reminder of the strange and fascinating nature of spacetime. The counterintuitive nature of the twin paradox, challenging our understanding of time. The twin paradox is a thought-provoking concept that challenges our intuitive understanding of time. At its core, the paradox highlights the strange implications of special relativity, forcing us to re-examine our assumptions about the nature of time. The counterintuitive aspect, time dilation and aging. The twin paradox seems counterintuitive because it contradicts our everyday experience of time. We expect time to pass at the same rate everywhere in the universe, regardless of motion or location. However, the paradox shows that time dilation causes time to pass differently for the traveling twin, resulting in a difference in aging. Why it challenges our understanding of time. The twin paradox challenges our understanding of time in several ways. 1. Relative time. The paradox highlights that time is relative, and its measurement depends on the observer's frame of reference. This challenges our classical notion of absolute time. 2. Time dilation. The paradox demonstrates that time dilation is not just a theoretical concept but a real effect that can be observed. This forces us to reconsider our understanding of time and its relationship to motion. 3. Aging and time. The paradox raises questions about the nature of aging and its connection to time. If time dilation can cause differences in aging, what does this say about the fundamental relationship between time and the human experience? Resolving the paradox. Embracing the weirdness of relativity. The twin paradox may seem counterintuitive, but it is a direct consequence of special relativity. To resolve the paradox, we must accept the strange implications of relativity and the relative nature of time. By embracing the weirdness of relativity, we can gain a deeper understanding of the universe and the complex relationships between space, time, and motion. The twin paradox serves as a reminder that our understanding of time is still evolving, and that there is still much to explore and discover in the realm of physics. Time dilation in movies and science fiction. A mixed bag of accuracy and artistic liberty. Time dilation, a fundamental concept in special relativity, has been a staple of science fiction for decades. Movies and TV shows often use time dilation as a plot device, but the accuracy of these depictions varies widely. Let's explore some examples of time dilation in science fiction, highlighting both accurate and inaccurate portrayals. Accurate depictions. 1. Interstellar, 2014. Christopher Nolan's film, accurately depicts time dilation effects on astronauts traveling through a wormhole. The crew experiences time passing normally, while time on Earth passes at a much faster rate. 2. The Time Machine, 2002. This adaptation of H.G. Wells' classic novel accurately portrays time dilation effects on the time traveler as he journeys to the year 800-2701. 3. Star Trek: The Next Generation. In the episode, The Inner Light, Captain Picard experiences time dilation effects while living an entire lifetime on a distant planet. The episode accurately depicts the consequences of time dilation on Picard's perception of time. Inaccurate depictions. 1. Back to the Future, 1985. While the movie's time travel concept is entertaining, it inaccurately portrays time dilation effects. Marty McFly's adventures in the past and future do not account for the significant time dilation effects that would occur during his high-speed journeys. 2. The Flash TV series, 2014. The show's depiction of time dilation is inconsistent and often inaccurate. The Flash super speed abilities would, in theory, cause significant time dilation effects, but these are rarely addressed or accurately portrayed. Artistic liberty versus scientific accuracy. Science fiction often prioritizes storytelling and entertainment over scientific accuracy. While some movies and TV shows strive to accurately depict time dilation effects, others take creative liberties to advance the plot or enhance the narrative. In conclusion, time dilation is a fascinating concept that has been explored in various science fiction stories. While some depictions are accurate and thought-provoking, others are inaccurate or inconsistent. By examining both accurate and inaccurate portrayals, we can appreciate the complexities of time dilation and the challenges of depicting it in science fiction. The impact of time dilation portrayals on public perception and understanding. The portrayal of time dilation in science fiction can significantly influence public perception and understanding of this complex concept. Accurate and thought-provoking depictions can inspire interest and spark curiosity, while inaccurate or misleading portrayals can perpetuate misconceptions and confusion. Positive impact, inspiring interest and curiosity. Accurate portrayals of time dilation in science fiction can 1. Inspire interest in physics and science. Movies and TV shows like Interstellar and Star Trek can motivate audiences to learn more about time dilation and its underlying principles. 2. Foster critical thinking and curiosity. Thought-provoking depictions of time dilation can encourage viewers to question their assumptions and explore the complexities of the concept. 3. Promote a deeper understanding of relativity. Accurate portrayals can help audiences grasp the fundamental principles of special and general relativity, including time dilation. Negative impact, perpetuating misconceptions and confusion. Inaccurate or misleading portrayals of time dilation can 1. Reinforce misconceptions and myths. Inaccurate depictions can perpetuate misconceptions about time dilation, making it more challenging for audiences to understand the concept accurately. 2. Create unrealistic expectations and misunderstandings. Misleading portrayals can lead audiences to believe that time dilation is more extreme or fantastical than it actually is. 3. Discourage critical thinking and skepticism. Inaccurate depictions can undermine critical thinking and skepticism, making audiences more susceptible to misinformation and misconceptions. Public perception and understanding. A mixed bag. Surveys and studies have shown that the public's understanding of time dilation is often incomplete or inaccurate. While some people may have a basic understanding of the concept, many others harbor misconceptions or misunderstandings. A 2019 survey conducted by the Pew Research Center found that only 22% of respondents correctly identified time dilation as a consequence of special relativity. 45% of respondents believed that time dilation is a result of gravity rather than motion. 21% of respondents were unsure or had no opinion on the matter. Conclusion: while accurate and thought-provoking depictions can inspire interest and curiosity, inaccurate or misleading portrayals can perpetuate misconceptions and confusion. By promoting accurate and engaging representations of time dilation, we can foster a deeper understanding of this complex concept and inspire the next generation of scientists, engineers, and critical thinkers. When encountering time dilation in media, ask yourself, 1. Is the representation accurate? Does the depiction align with our current scientific understanding of time dilation? 2. What creative liberties have been taken? Are there any exaggerations, distortions, or omissions that might impact the accuracy of the representation? 3. What message is being conveyed? Is the portrayal of time dilation used to explore complex scientific concepts, or is it primarily employed for dramatic or entertainment purposes? 4. What are the implications of this representation? Does the depiction of time dilation dilation have any broader implications for our understanding of space, time, and the universe? By cultivating a critical eye for time dilation in media, you'll become more discerning and informed consumers of scientific information. This critical thinking will serve you well in evaluating not only time dilation, but also other complex scientific concepts. Time dilation, key takeaways and real-world implications. As we've explored the fascinating concept of time dilation, here are the key takeaways and real-world implications to remember. Key takeaways. 1. Time dilation is real. Time dilation is a fundamental aspect of special relativity, and its effects have been experimentally confirmed. 2. Time is relative. Time dilation demonstrates that time is relative, and its measurement depends on the observer's frame of reference. 3. High-speed motion and gravity cause time dilation. Time dilation occurs when objects move at high speeds or are placed in strong gravitational fields. Real-world implications. 4. GPS technology relies on time dilation corrections. GPS satellites must account for time dilation effects caused by their high-speed motion and altitude. 5. Particle accelerators and high-energy physics. Time dilation plays a crucial role in particle accelerator experiments, where high-speed particles experience time dilation effects. 6. Astronauts and space travel. Time dilation effects will become more significant as astronauts travel to distant stars and experience high-speed motion and strong gravitational fields. 7. Time synchronization and telecommunications. Time dilation effects must be considered when synchronizing clocks across different locations and in telecommunication systems. By understanding time dilation and its real-world implications, we can better appreciate the complex and fascinating nature of spacetime. The mysteries of time and space continue to intrigue and fascinate us. As we delve deeper into the intricacies of spacetime and the nature of gravity, we are reminded that there is still so much to explore, to discover, and to understand. As we ponder the wonders of the universe, we are left with a profound question. What lies beyond the boundaries of our observable universe, where the fabric of space-time is stretched to its limits, and the laws of physics, as we know them, begin to break down? This question invites us to contemplate the unknown, to speculate about the nature of reality beyond our cosmic horizon, and to inspire new generations of scientists, philosophers, and explorers to continue pushing the boundaries of human knowledge. Potential applications of time dilation in future technologies. Time dilation, a fundamental concept in special relativity, has far-reaching implications for various fields, from space exploration to telecommunications. As our understanding of time dilation deepens, we can expect to see innovative applications in future technologies. Potential applications. 1. Deep space exploration. Time dilation can be leveraged to facilitate longer-duration space missions. By traveling at high speeds or utilizing gravitational time dilation, astronauts could experience time passing more slowly, allowing them to travel farther and stay in space for extended periods. 2. Advanced propulsion systems. Time dilation could be exploited to develop novel propulsion systems, such as those utilizing exotic matter or energy. These systems could potentially enable faster-than-light travel, or more efficient propulsion methods. 3. Quantum computing and cryptography. Time dilation can be used to enhance the security of quantum communication systems. By utilizing time dilation effects, quantum keys can be generated and distributed more securely, enabling more robust encryption methods. 4. Telecommunications and synchronization. Time dilation effects must be considered when synchronizing clocks across different locations, particularly in high-speed telecommunication systems. By accounting for time dilation, more accurate and reliable synchronization methods can be developed. 5. Advanced materials and manufacturing. Time dilation can be used to create novel materials with unique properties. By manipulating time dilation effects, researchers can create materials with tailored characteristics, such as superconductors or nanomaterials. 6. Medical applications. Time dilation can be used to develop new medical treatments, such as those involving high-speed particle beams or advanced radiation therapy. By leveraging time dilation effects, medical professionals can create more precise and effective treatments. 7. Astronomical observations. Time dilation can be used to enhance our understanding of celestial phenomena, such as gravitational waves or black hole physics. By accounting for time dilation effects, astronomers can gain more accurate insights into the behavior of celestial objects. Challenges and limitations. While time dilation offers exciting possibilities for future technologies, There are challenges and limitations to consider. 1. Scalability. Time dilation effects are typically only significant at very high speeds or in extremely strong gravitational fields. Scaling these effects up to practical levels remains a significant challenge. 2. Energy requirements. Manipulating time dilation effects often requires enormous amounts of energy, which can be difficult to generate and control. 3. Stability and control. Time dilation effects can be unstable and difficult to control, particularly in complex systems. Time dilation is a fascinating phenomenon with far-reaching implications for various fields. While there are challenges and limitations to overcome, the potential applications of time dilation in future technologies are vast and exciting. As our understanding of time dilation deepens, we can expect to see innovative breakthroughs and discoveries that will shape the course of human history. As we conclude our journey through the fascinating realm of time dilation, we encourage you to continue exploring the intricacies of this phenomenon. Delve deeper into the world of relativity and discover the many wonders that await you. Call to action. 1. Share your thoughts. Join the conversation on social media using the hashtag #TimeDilationExplain. Share your thoughts, questions, and insights about time dilation and its implications. 2. Explore further. Visit online resources, such as NASA, link Unavailable, or Khan Academy, to learn more about time dilation and relativity. 3. Spark curiosity. Share this video with friends, family, or students to inspire curiosity and exploration of the fascinating world of physics. 4. Join the discussion. Participate in online forums, such as Reddit's r, Physics or r, Ask Sense, to engage with experts and enthusiasts, and to explore the latest developments in time dilation research. By continuing to explore and discuss time dilation, we can collectively deepen our understanding of this phenomenon and its far-reaching implications for our understanding of the universe. Thank you for watching. We appreciate your interest in time dilation and relativity. If you have any further questions or topics you'd like to explore, please let us know in the comments. Stay curious, keep exploring,